Yes. So, in general, we should distinguish between three kinds of degrees of freedom. We have the gravitational field that will go with us all the way. I mean, the different modes of it would be eliminated along the way, but it will be there until we eliminate it completely. And it's worth mentioning that once one leaves the point mass approximation, then one needs to consider coupling to the tetrad field, because we don't have a way to couple to the metric directly. We do it with the tetrad field. So this would represent the gravitational field. Once one starts to consider spin and higher multiples. The second kind of degree of freedom that we identify is the one that represents the particle world-line coordinate. We will use the time coordinate to be our affine parameter in every computation that we will do. So basically, we are worried about what is the three vector position represents, and in that context, it's important to note that the tricky thing is that the particle world-line position does not in general coincide with the object center. So that's the tricky thing that one has to handle once one leaves the point mass approximation. Because when we just have a point mass, there is no ambiguity. The coordinate of the world-line is just represents our particle, and there's no ambiguity. But once one starts to consider a spin, then we start having an ambiguity, because a spin necessarily means that we cannot actually handle something which is point particle. It has to have a finite size. And that's just the result of GR, or even of special relativity, basically. That if you have a given spin, a finite spin, and you don't want the rotational velocity to be superluminal, that means that you have the object, you cannot take the object size to be 0. And that gives you a bound for the size of the object, and this bound is actually what we know as the Kerr horizon. This is the bound for the size of the smallest rotating object that we have in relativity. So that's the tricky part that actually one should address. And I was talking yesterday to Shangling and trying to stress this point that to me that's still like conceptually not a question that is completely figured out. Okay, and the last kind of degree of freedom that we should have is the particle world-line what represents the rotation, rotating degrees of freedom of the particle on the world-line. So we start by considering the world-line tetrad. From this world-line tetrad, we define the angular velocity, and we find it inevitable to define its conjugate quantity, which is the spin, that we use as a classical source on the world-line. So we start by considering the world-line tetrad, that's simple, but then we move to having an angular velocity and the conjugate spin. And then again, in order to make this disentangling between particle degrees of freedom and gravitational degrees of freedom, we should switch again to local Lorentz matrices, which will represent the rotation around the locally flat frame. So finally, our rotating degrees of freedom will be Lorentz matrices and the conjugate local spin, which will be the spin projected again to the locally flat frame. So you can see already that there are like, this is a subtle issue once you start considering rotation. Now, the second thing that we have to identify correctly is what are the symmetries we're coming to today. And the most trivial thing, when you just consider a point mass, we just know that we have to have general covariance and reparameterization invariance. That's very simple. We have that in the point mass case. But the point is that if we want to say something new once we leave the point mass approximation, once we start considering spin, we have to think some more. We have to take other symmetries into account. And that's, again, what our work added with respect to all previous works that were there before. And using these additional observation, additional symmetry that we stressed, we were able to say more about the action of the spinning particle. So there is the parity invariance, which plays a key role in constructing the non-minimal coupling part of the action. There is the internal Lorentz invariance that allows us to have some gauge choice of the field tetrad, the local tetrad that will cover all the manifolds. We have the SO3 invariance of the body-fixed spatial triad. And there is something which is rather tricky, the thing that represents this freedom to choose the center in the spinning particle that I was trying to describe earlier, that we dubbed as a spin gauge invariance. And that is the invariance, what we actually, our discovery was that the freedom to choose the point within the spinning particle amounts to the freedom to choose what would be the time-like vector that would complete the spatial triad into a tetrad. So that's the freedom that we have. We can have different, we can boost this vector, and this will correspond to different choices of center of the spin. The last assumption that we made is that we just assume that the isolated object has no intrinsic permanent multiple moments beyond the mass and the spin, so that when we analyze the non-minimal coupling part of the action, we would only have in mind what is induced from having the spin. The quadrupole that is induced by spin, the hexadecapole that is induced by spin, and so on. We don't think about any intrinsic quadrupole structures of stars or at this stage. We want to focus on the effect of spin. Okay. So, as I said, we start by thinking about the one particle EFT. And first, we have the effective action of the spinning particle. And people have thought about it already. Actually, they started thinking about it in the context of special relativity. And this is like the seminal work of Hanson and Reggie from 1974. And already in 1975, there was this work that they did for curved space-time. And these works already considered the trivial symmetries that I was mentioning earlier, which is general covariance and reparametrization invariance. So if you just define the coordinate velocity and the angular velocity that I was mentioning earlier, just defined from the word like tetrad by a usual generalization of the special relativity basically definition, one gets that the point particle Lagrangian should be a function of u, omega, and the metric field. And we define the conjugate, the spin, as the conjugate of the angular velocity. And it's convenient for us also in the context of EFT to have this spin because we want to think about it as a classical source on the world line, which will emit gravitons. So this is something important that one should have in mind, that we actually switch from having one degree of freedom that describes rotation to having 2 degrees of freedom, which are conjugates, which already kind of says to us something about being in a canonical Hamiltonian kind of area. Something is related to canonical structure because we're considering 2 conjugate degrees of freedom to describe rotation. And so this, as I said, these seminal works already go to the conclusion that the general form of a spin particle action should be the following. Should be this part that represents just the minimal coupling. Just the the usual part that represents the motion of the point mass and the part that represents the minimal coupling of rotation. But then we will have an addition, which I denote here by SI, namely the non-minimal coupling part, which is spin-induced, the higher multiples, which are induced by having spin. And this in general will be a function of U, of S, and of metric-related quantities like Riemann, covariant derivatives, and so on. So our work focused on what we can say more about this part of the action, about the minimal coupling part rotating, and what can we say about the non-minimal coupling part, because this, again, was something that was not addressed before. Can we constrain, can we say something about it? Because this, as I said, this general form was already known many decades ago. There was nothing new that EFT has done to this point, to the point that our work entered. And then another important thing to have in mind is that for an EFT with spin, the gauge of both rotational variables should be fixed at the level of the point particle action. The point is that unless one fixes the gauge of the rotational variables, separation of the field and particle degrees of freedom cannot be obtained. So if we want to indeed integrate out all the field degrees of freedom, we should, before integrating out, we should gauge fix the gauge of the rotational variables. So in general, the assumption that everybody starts with, if it includes us, we start from the assumption that we are in the covariant gauge. So basically this form of the action is assuming that we are using the covariant gauge for the rotational variables. The covariant gauge says that the time-like vector of the triad is orthogonal, not orthogonal, sorry, is parallel to the momentum of the object, and that the spin and the momentum are orthogonal. Okay. The first thing that we do, I will start with a little bit sketchy here, and I will tell more details in the coming lectures. So the first thing that we do is that we want to introduce the gauge freedom of rotational variables back into the action. So from having this term only, we want to, and using the covariant gauge, we want to go to something more general. So what we do is we think about the time-like vector of the tetrad, which is given in some choice of time-like vector, and we make a boost-like transformation to this vector, of course in covariant form, something that keeps covariance, and then we get to a generic gauge. Okay, we get a generic gauge that puts in a new gauge variable for the time-like vector, and we get a generic gauge for the spin variable. That's the most generic way to write what are the possible choices, to constrain the spin variable. When we do this exercise, it's a simple exercise that we put in our paper, we get the following result. We get the result that an extra term in the action appears. So from this term, we get something new, which is in this form. A new spin variable, new variables, but now we have this term and another extra term in the action appears. And that's this term. And both of them originate from minimal coupling. So we have this extra term here that contributes to finite size effects, but it carries no Wilson coefficient. This term is not preceded by some unknown coefficient. And the point is just to realize that it doesn't represent any UV physics that we want to account for. It just represents for the fact that once we move to a spinning object, we have a finite size. And that is true for whatever UV physics that one will have. Therefore, you would have to have this correction that will contribute to finite size effects. And then what we will do on all the terms which will appear beyond minimal coupling, we'll just switch from the generic spin variable, from the spin variable that was in the covariant gauge, we will switch to the generic spin variable. So that will be our way to change in general, the action. Now, the non-minimal coupling of the action with spin, it must and can be constrained using all the symmetries that we observed earlier. And generally, the way to construct this action would be just to know that the building blocks would always be a product of two ingredients. One would be the spin-induced higher multiples, which would have, after analysis, we would get to the conclusion that they would have a very, very simple form, and they would always be contracted by some Riemann-dependent operator. It can be Riemann, and then we can add to it some covariant derivative, but that would be the general structure that would go all the way. And what will constitute our spin-induced higher multiples would be just the spin vector, and the spin vector is just defined from the dual of the spin tensor, as you can see here. It's very simple. From the spin vector, we define the related scalar, which is the spin square. And only by using the following symmetries that I noted earlier, which are the SO3 variants of the body fixed triad, and the fact that we initially start from the covariant gauge, we would get to the conclusion that the spin-induced higher multiples, they are symmetric, they are traceless, they are spatial, and they are constant tensors in the body fixed frame. And therefore, they would be, the general structure of these spin-induced higher multiples would just be direct products of